Welcome back, everyone. Today we're diving deep into a really fascinating paper about analyzing those massive, the really huge whole slide images used in pathology, like when they're diagnosing cancer. I mean, these images are just gigantic billions of pixels, not exactly easy to just, throw at a computer and say, figure it out.
Oh, absolutely. And the way we're mostly handling that right now, it's this thing called bag-based multi-instance learning, MIL for short. And it's kind of like, imagine each of those giant images as a bag, right?
Yeah.
And inside are all these smaller instances, which are basically patches of the whole thing.
Patches, gotcha. So instead of looking at like the entire slide at once, you're breaking it up into these smaller chunks, I guess.
Exactly. But here's the thing. Usually, we only have a label for the whole bag, the whole slide, like yes, cancer, or no cancer, but nothing for the individual pieces. So the algorithm has to figure out from these little glimpses what's going on in the whole thing. Weekly supervised learning, it's a challenge.
Okay, so it's like you've got this huge box of Legos and you're trying to find one specific rare piece, but you can only grab handfuls of bricks at a time, and you only know if that special piece is somewhere in the box, not which handful.
A perfect analogy. So how do we do this now? Well, there's this two-step process. First, you've got to extract features from all those little patches. Usually we use a pre-trained neural network for that, something that's already learned to recognize patterns in images, at least in a general sense. Then step two, we use MIL algorithms to take all those features, put them together, and try to make a prediction for the whole slide, the whole bag. Does it have the cancer piece or not?
Makes sense, but I'm guessing there are some problems with this two-step approach, right?
You bet. The paper we're looking at today, MsaMIL-Net, an end-to-end multi-scale-aware, multiple-instance learning network for efficient whole-slide image classification, they point out a big one. That separation between feature extraction and MIL, it's not ideal. Because the feature extractor, it's kind of blind to the big picture, right? It doesn't know that MIL is waiting down the line, trying to make a diagnosis. So the features it learns, they might not be the most useful ones for that specific task.
So it could be learning things that are just kind of irrelevant to whether or not there's cancer present.
Could be, yeah. And there's another issue. These feature extractors, they often operate at a fixed magnification. Like they're always looking at the patches, it's a 20x zoom. But real pathologists, they don't do that.
No, they're constantly zooming in and out, right? Checking the overall structure, then looking at specific cells in detail.
Exactly. It's not just about seeing more. Each magnification gives you a different kind of information, so a single-scale approach, it misses out on that. Plus, you're wasting time and computing power on areas that might be totally irrelevant to the tumor, if there even is one.
So you're saying we need a system that can look at these slides more like a human pathologist would at multiple scales, and also make sure the features it extracts are actually useful for making a diagnosis.
That's the idea. And that's where this paper gets really interesting. They propose this new framework, MsaMIL-Net. And it's all about doing multi-scale feature extraction and the MIL aggregation together, all at once, end-to-end, they call it. That way, those two parts can learn from each other during training.
Oh, I like that. So instead of training them separately and hoping they'll work well together, you're letting them figure it out as a team.
Exactly. And they've got some clever modules to make this happen. First, there's the semantic feature filtering module, SFFM. Think of it as a quick scan, like a pathologist taking a first look at low magnification. This module does a pre-segmentation step on a low-res version of the whole slide and creates a mask highlighting where the potential problem areas are.
A mask. So basically, it's drawing a rough outline around the parts that might be a tumor, so the system knows where to focus its attention.
Precisely. Then comes the multi-scale feature extraction module, MSFM. This is where it gets that multi-scale aspect.
Yeah.
The module extracts features from those pre-filtered patches, but it does it at 3 different magnifications, 20x, 10x, and 5x, just like a pathologist would.
Okay, that makes sense. Capture information at different levels of detail. And then what happens?
Then they've got this multi-scale fusion MIL module. They also call it the Instance-Aware Attention Module, or IAMM later on. This takes all those multi-scale features and combines them, weighs them, aggregates them, all that good stuff. And finally, it spits out a prediction for the whole slide. Is it cancerous or not?
Awesome. And do they have any, results to back this up? Does it actually work better than the old way?
They do. And it does. They tested MsaMIL-Net on 3 different publicly available datasets. DigestPath 2019, that's for colonoscopy images. BCNB for breast cancer metastasis. And UBC-Ocean for ovarian cancer subtypes. And on all 3, it beat the current state-of-the-art methods, both single-scale and multi-scale.
Wow, that's impressive. Okay, so before we dig deeper into exactly how this all works, I think it's helpful to take a step back. Why did we even end up with this two-step MIL approach in the first place? Like historically, how did we get here?
Good question. WSI analysis, it's come a long way. I mean, way back, it was all manual. Pathologists looking at slides under a microscope. Then we got the tech to digitize those slides, boom, WSIs. But these digital images, they're huge, gigapixels. You couldn't just, use the normal image analysis techniques. Computers couldn't handle it.
So the whole divide and conquer approach, breaking the slides into patches, that was born out of necessity.
Absolutely. And then the question became, okay, how do we make a diagnosis for the whole slide when we only have that one label for the whole thing? That's where MIL came in. At first, researchers, they'd often grab these pre-trained feature extractors from the general computer vision world. Things trained on ImageNet and all those everyday object data sets. They hoped those features would work for pathology too.
So kind of like borrowing tools from a different field and hoping they'd be useful here.
Yeah, exactly. But over time, it became clear that medical images, especially WSIs, they're kind of unique. Their features, the patterns that matter, they're different from, recognizing cats and dogs. So people started working on more domain-specific feature extractors, even using self-supervised learning techniques, things like DINO, the icon, CTranPath, and the paper mentions those. All about learning directly from unlabeled pathology data. No need for those manual labels.
So getting more specialized, more focused on the specific task. But as the paper points out, even with these fancy feature extractors, the MIL training, it's still kind of separate, right?
Yeah, that's the issue. It's like you train this model to be good at image recognition in general, and then you hope it'll magically be good at spotting cancer patterns when you feed it to the MIL. Reasonable starting point, but not the most efficient, and it might not fully leverage the potential of either part.
It's like you're training a chef to make amazing sauces, but then you throw them into a bakery and hope they can instantly decorate a cake.
Exactly. And there's the whole magnification thing we talked about. Pathologists, they use multiple magnifications, right? So researchers started developing multi-scale MIL approaches, trying to use information from different zoom levels. There's CSMAL, MIL-Booster, HIPP, those were early attempts. But they have their own limitations, like how to really model those cross-scale relationships effectively.
So it's not just about stacking different magnifications together. You need a way to make them work together, learn from each other, right?
Right. And the aha moment was realizing to really do this right, to mimic how pathologists work and get the best performance, you need to bring it all together. That's why this end-to-end training idea is so significant.
Makes sense. So back to MsaMIL-Net. It's building on all this history, trying to solve these limitations. Let's get into the nitty-gritty. How does this end-to-end multi-scale learning actually work? They call it a hierarchical feature refinement pipeline.
Yeah, and the beauty of it is the whole thing is end-to-end differentiable. That means during training, the network knows how every part from that initial feature filtering to the final diagnosis affects the outcome, so it can learn and adjust much more efficiently.
So it's not just learning in isolation, it's learning how all the pieces fit together.
Exactly. Okay, let's break it down. First, that semantic feature filtering module, the SFFM, it uses a UNet++ segmentation network. Now, UNet++ WOM, it's kind of an upgraded version of the regular UNet. UNet is this really popular architecture for image segmentation, especially in medical imaging. UNet++ takes that and adds some bells and whistles, like different depths of these UNet-like structures, connections between different parts, that kind of thing. It tends to give more accurate and reliable segmentation results.
So better at drawing that initial map of the potentially cancerous areas. Why is that so important?
Because that mask, it guides the rest of the process. Remember, these WSIs are massive. By focusing only on the areas that might be a tumor, we can save a ton of computation.
How much are we talking? Is it a significant difference?
Oh, definitely. In their ablation study, they found that using only the pre-segmented lesion areas made the processing time way faster compared to using all the patches, like significantly faster. And get this, it actually improved the accuracy a bit too, compared to using all patches. And it was way better than just randomly picking patches.
Wow, so it's not just about speed, it's about focusing on the right information, cutting out the noise.
Exactly.
Yeah.
Okay, next, the multi-scale feature extraction module, MSFM. Those filtered patches, no matter their original magnification, they get resized to 512 pixels. Then they're fed into an efficient NetB3 backbone.
Efficient net, that rings a bell. It's one of those super efficient convolutional neural networks, right?
Yep. They're known for being really good at image tasks, but with fewer parameters and less computation. So a good choice here. But then They add an extra layer, transformer encoder. Transformers, they're all the rage now, and for good reason. They're great at capturing these long-range dependencies in data. So after EfficientNet extracts those local features from the patches, the transformer can look at the whole patch and figure out how those features relate to each other. It's like going from understanding individual words to understanding the whole sentence.
Got it. Get a more holistic view. And they share the network parameters across all three magnification levels, right? 20x, 10x, 5x. What's the point of that?
Good catch. Sharing parameters, it forces the network to learn features that are consistent across scales. Like a certain cell structure, it might look a bit different at 20x versus 10x, but fundamentally it's the same structure. Shoulding weights helps the network learn that fundamental representation, and then it can just fine-tune it for each specific scale. Plus, fewer parameters overall, which means less data needed for training, better generalization, all that good stuff.
It's like learning a concept and then just adjusting your perspective to see it at different scales.
Perfect analogy. Okay, so now we've got all these multi-scale features. What happens next? That's where the Instance-Aware Attention Module, IAAM, comes in. It's got two main parts, the Multi-Scale Hierarchical Encoder, MHE, and the Dynamic Multi-Instance Query, DMQ.
Let's start with the MHE. What does it do?
So it takes those multi-scale features, but it also adds some extra information. The relative position of each patch within the whole slide and the original magnification.
Why is that important? Like, why tell the model where the patch came from and at what zoom level?
Because context matters. The spatial arrangement of cells, tissues, all that, it's crucial for diagnosis. And the scale at which you observe something can also change its meaning. By telling the model, hey, this patch is from the top right corner and it was originally at 10x, it gives it more information to work with. Plus, they arrange the features in a specific way, grouping those from different scales with the same spatial region close together. This helps the attention mechanism understand the relationships between features at different magnifications, but coming from the same area of the tissue.
So it's not just seeing a bunch of random features, it's seeing them in context, spatially, and scale-wise. Makes sense. And then there's this multi-head low-rank attention, MLA. You mentioned earlier that attention can be computationally expensive. How does this low-rank thing help?
Good memory. So standard attention, the way it calculates relationships between things, it can get really complex, especially with lots of data. Low-rank attention, it's a way to approximate that, to simplify it. It focuses on the most important connections, the strongest relationships, and ignores the weaker ones. Like summarizing a book by focusing on the key sentences, not every single word. It makes the process much more efficient, especially with these large WSIs.
Gotcha. So it's like a smart shortcut, but without losing too much information. And then we have the DMQ, the dynamic multi-instance query. They mentioned this issue of like having different numbers of patches at different scales.
Right, because even after filtering, you'll usually have way more high magnification patches than low magnification ones.
Yeah.
So if you just combine everything equally, the high-res stuff might drown out the low-res stuff, which might have important information too.
Like you might miss the forest for the trees.
Exactly. So the DMQ, it uses these learnable embedding vectors as queries. They're like little probes that search through all the multi-scale features and pick out the most informative ones, regardless of the original magnification or how many patches there are. Then, a gated attention layer weighs those selected features and fuses them into one representation for the whole slide.
So it's like a smart filter, making sure the important stuff gets through, even if it's rare.
Exactly. Okay, let's talk training. They do this two-phase approach. First, they train the entire MsaMIL-Net end-to-end using all the non-background patches. It's like a general training session, getting everyone warmed up and working together.
Get the basics down. And then phase 2.
Then, they focus on fine-tuning. They use only the features extracted from those precisely identified lesion areas from the SFFM. So it's like, okay, now that we've got the basics, let's zoom in on the really important parts and get even better.
Makes sense. Focus on the details. And they use some tricks like gradient checkpointing and accumulation, right? I remember you mentioned those before.
Yeah, those are essential for training such a huge model on those massive images. It's all about making the training process more efficient, using memory more smartly, so we can actually fit it all on the hardware we have.
Clever. Okay, the results. You already mentioned they beat the state-of-the-art on 3 different data sets. That ablation study with the lesion segmentation, it really shows the value of that SFFM, both for speed and accuracy.
Totally. And their end-to-end training, it beat a more traditional approach using Dyno self-supervised pre-training. Not only in terms of accuracy, but also training time. So it's more accurate and faster.
Double win. Okay, let's recap the key contributions here. This end-to-end training of a multi-scale feature extractor and MIL network, that's a big deal, allows for true joint optimization. The pre-segmentation with the SFFM, huge for efficiency without sacrificing accuracy. And extracting features from those native patches at multiple magnifications, just like a pathologist, that lets the model get a much richer understanding of the tissue. Plus, the IAM, with its smart querying, makes sure all those multi-scale features are used effectively for the final diagnosis.
Absolutely. It's addressing some really fundamental limitations in WSI analysis.
And what about the real-world implications? If this works as well as it seems, what does it mean for pathologists and patients?
Potentially, a lot. Faster, more reliable diagnoses, which means earlier treatment. The reduced computational cost that makes it more accessible to more hospitals, even those without fancy equipment. And the fact that it aligns with how pathologists already work, that could lead to more intuitive and clinically relevant AI tools. Personalized medicine, treatment planning, all that.
That's exciting. It feels like this could really change things. Okay, let's move on to our novel notions segment. What are some future research directions that build on this work? What could we explore next?
One cool idea is dynamic magnification learning. So MsaMIL-Net uses those 3 fixed magnifications. But what if the model could learn which magnifications are best for each specific slide, or even each specific region of a slide?
Like it could decide, hey, for this area, I need to zoom in a bit more, maybe to 15x to really see what's going on.
Exactly. Different cancers, different stages. They might have features that are most visible at non-standard magnifications. We could use reinforcement learning to train a model that learns to zoom to the most informative scales. That could make the analysis even more efficient, and we might discover new biomarkers that we're missing now because we're stuck at those fixed magnifications. Of course, it'd be tricky to implement, but super interesting.
That's a wild idea. I love it. What else?
Another one is using graph neural networks to model the relationships between patches more explicitly. MsaMIL-Net uses attention, which is good, but GNNs, they're specifically designed to model relationships between things.
So how would that work here?
We could represent each patch as a node in a graph. And the connections between those nodes, the edges, they encode information about spatial proximity, scale difference, even learned relationships between the features. The MHE in MsaMIL-Net already considers spatial arrangement, so that could be a good starting point. GNNs might be better at capturing the overall tissue architecture, like the arrangement of glands or immune cells, which can span multiple patches and scales. Could lead to better detection of things like metastasis, better understanding of the tumor microenvironment, and ultimately more accurate prognosis. Of course, GNNs can be computationally expensive, so it's a trade-off.
Those are some really cool ideas. This whole paper, it's a big step forward in using machine learning for WSI analysis, end-to-end multi-scale learning, efficient filtering. It's a powerful combination.
Absolutely. And it opens up all sorts of possibilities for the future.
Well, for those of you who want to dive deeper into the technical details, we've got a link to the paper in the description. And as always, remember, our novel notions are just speculative ideas meant to spark discussion. Actual research might go in totally different directions.
That's the fun part.
Exactly. Thanks for joining us on this deep dive. We'll be back soon with another exciting paper. Until then, keep learning, keep exploring, and we'll see you next time.
See you then.